Okay, so since I'm new to most of you here, so please allow me to make a brief introduction on my research interest. So I'm mainly interested in the topological band theory and DFT calculations on both electronic and phono-related properties. And in my research, I use DFT calculations as the bridge to connect the condensed matter theory and the condensed matter experiments. So in the following, I will give a brief introduction on my research on the topological band theory and the DFT calculations on topological electronic materials. And then I will move on to the final topic. So about the topological band theory, the most famous material is the topological insulator. So what is topological insulator? So let's first start with the trivial insulator. So trivial insulators have a band structure like this, and it have a finite energy gap. So which means that the Fermi level is in between this gap, and it have a low conductivity in both the bulk and the surface. But for the topological insulators, although it is still an insulator because there is energy back in the bulk, but on the surface there will be something different, because on the surface there will be topological surface states connecting the conduction band and the valence band, so the surface state will be metal-like, which means that it will have a high conductivity on the surface. And at the same time, the topological surface states will be protected by the topology of the system. So they will be robust to the impurities and defects, and so the topological materials are ideal candidates for the low-loss devices. As for the classification, there are various topological states for the topological materials, and they can be defined in both the insulator systems and the same metals. And the topological invariant is the key to catalog and diagnose different topological materials. So in the past several years for the topological band theory, so we complete the classification of different topological states for all the space groups, and we built the mapping between the topological invariant, topological surface states, and the symmetry-based indicators. And this theory greatly reduced the calculation for diagnosing topological materials by the DFT calculations. So hereafter, by using the first theory, so we designed an algorithm and conduct a high throughput calculation on all the materials in the database. And then we discovered more than 8,000 topological materials and built the first topological electronic material database. So if you have a very interesting material and if you want to check the topology of this material, you just click this website and check the topological information. Oh, okay, so at the same time, we keep predicting new topological electronic materials and collaborate with the experimental groups to verify them, including the APAS, STM, and so on. So this is my work in the topological electronic materials. So let's move on to the final topic. So since the previously two speakers have stressed the importance of phonon in condensed matter physics, so I just skip this part. And I would like to talk about the topology and the chirality in phonons. So because phonons are as important as other quasi-particles like electrons in condensed matter physics, but phonons have very limited degrees of freedom to control. For example, phonons are charge neutral, spin zero, and orbital free. So we need to introduce new degrees of freedom to the phonon spectra. So based on my background, which is topological band theory, we know that one of the famous topological quasi-particle is well-forming. And the well-forming is both chiral and topological in addition to the charge, spin, and orbital degrees of freedom. So our idea is to introduce the topological band theory from the electronic systems to the phonon systems, and then introduce both topological and chiral degrees of freedom to the phonon spectra, and corresponding to the topological phonons and chiral phonons. However, those two directions were developed independently in the past, but they can be merged together in the systems with well phonons, since well phonons are both chiral and topological. So in the following, I will use the chiral phonons as examples to show both the topological and chiral degrees of of freedom in the phonon spectrum. So the topological degrees of freedom for wave phonon is described by the chain number, and the sign of the chain number, which can be plus or minus, reflects the k-space chirality of wave phonon in the k-space. Yeah, because the chain number is calculated by the integral of wave function in the k-space. And at the same time, if the Hamiltonian describing the wave phonon preserves the Chiral symmetry, then we can define the pseudo spin texture for each of the wave band. And the wiping number for the pseudo spin texture swapping out the sphere enclosing the wave phonon will equal to the chain number, which means that the pseudo spin texture also reflects the k-space chirality for wave phonons. And at the same time, if the chain number is non-zero, then there will be topological surface states for wave phonons, which is in a helicoid shape. So such kind of helicoid surface state also shows the k-space chirality. And the topological surface states will always connect a pair of wave phonons with opposite chain number. And the surface state will show different chirality near different wave phonons. So the first wave phonon was predicted in the I-silicon family, which has a chiral-cubic crystal structure. And here is the Berlin zone, which is also in a cubic shape. And the green plane is the surface Berlin zone along this 001 direction. And this is the phonon spectrum for the I-silicon material. So if we focus on the highest side of the optical phonon mode, we can notice that there are two wave phonons located at gamma point and R point, with a chain number of +2 and -2 respectively, because those two wave phonons have opposite sign, so they have opposite chain number, opposite chirality. And also because those two wave phonons have the multiple charge of 2, so we also call them double wave phonons in our paper. So I would like to note that for all the chiral crystals, yeah, including the alpha phase mercury sulfur and the tellurium and this family. So the acoustic phonon is always a double wave phonon, which means that the chain number for the two transverse acoustic modes are always +2 and -2. Okay, so let's move on with the surface state calculation. If we make this material a finite slab with an open boundary condition along this 001 direction, then there will be surface states in addition to the bulk dispersion. So on the 001 surface Berlin zone, the double wave phonon located at gamma point will projected onto the surface Berlin zone center, and the wave phonon at R point will projected onto the surface Berlin zone corner. And the yellow shades are the helicoid surface states. And if we have as an energetical counter like the Fermi surface in the electronic systems, then we will have a surface arc crossing this helicoid surface state. And this surface arc will connect the two wave phonons with opposite chirality. And if we change the energy, this surface arc will rotate around those two wave phonons, show the k-space chirality. Okay. Yeah, because of the symmetry. It is. Can I answer this question after I finish the talk, because there are like 13 pages. Okay. Yeah, sorry. Yeah, so let's move on first. So our prediction was soon verified by our inelastic X-ray scattering collaborators in Brookhaven National Lab. So here the experimental data and the DFT calculations matches each other very well for the phonon dispersion. So which demonstrate the existence of two kinds of double wave phonons in this I-silicon. So after we introduced the k-space chirality, let's move on to the R-space chirality, which corresponds to the atomic motion in the real space, and they can be linearly polarized, circular polarized, and even with certain atoms keep stationary. And it is totally dependent on the wave function of the phonon, and you can see the details in our paper. So people use angular momentum to describe the k-space chirality of phonons, which are to describe the phonon polarization. So if the wave function have a non-zero angular momentum, then there will always be the circular polarized atomic motions in the real space. And this is also the most widely exist Phonon modes in solids, which might be counterintuitive for most of us. Yeah. And the circular polarized phonons has a very long history for study, and they were called the circular polarized phonon or rotational vibration in the last century, and they were also called Chiral phonons in the recent years. Okay, so if we consider other additional symmetries like time reversal symmetry, mirror symmetry, then the additional symmetries will restrict the angular momentum to be zero, which is also discussed in our paper here. And in this case, if the Phonon mode with zero angular momentum, then there will be three possibilities for the atomic motion in the real space. Yeah, the most common one is the linear vibration. Okay. So here I will use still use the iron silicon to show the R-space chirality for the well phonon. For example, so those three movies are the atomic motion for three phonon branches with different chain number. For the acoustic phonos in I-silicon, for example, the phonon mode with chain number of +2, it will have a counterclockwise atomic motion corresponds to the right-hand chirality, while the phonon mode with chain number of -2 corresponds clockwise atomic motion, which have a left-hand chirality. While the phonon mode with chain number of 0, it has a linear vibration, so it is non-chiral. So up to now, we have discussed the topology and chirality of well phonons, and in this comment paper this year, we have discussed the topological and chiral degrees of phonons in well phonons, and the chirality of phonon can be understood in both K space and R space. Okay. So now we have introduced both topological and chiral degrees of phonon, but here may raise up a question, which is how to observe the phonon topology and chirality. Also, from my background in the topological band theory, so people show that so we can use the eigenvalue of the rotational operator to calculate the chain number of the well phonon. So similarly, in the chiral phonon field, we have the pseudo-angular momentum, so which is defined to reflect the eigenvalue of the rotational operator, which means that the rotational symmetry or the pseudo-angular momentum can diagnose the topology and the chirality of well phonon. So which Professor Zhang and Professor Sato has introduced in their talk. So in the following, I will also give material examples. So let's make a brief summary here. So by introducing three physical quantities, like chain number, like angular momentum, and the pseudo-angular momentum, we have briefly introduced the topology and the chirality in phonons. Yeah, but the angular momentum and the pseudo-angular momentum are different physical quantities, so they are not inherently related. So if we want to build the connection, or if we want to use the pseudo-angular momentum to identify chiral phonons, then the DFT calculations or symmetry analysis is necessary. So in the following, I will show you the comprehensive study for the symmetry constraints of the general chiral phonon and how to use the pseudo-angular momentum to identify chiral phonons. So in our recent work, so we have studied the phonon degeneracy, the phonon angular momentum, and the pseudo-angular momentum, and associated physical phenomena. So under three types of magnetic point groups, and we discovered that the angular momentum are highly dependent on the symmetry of the system. So in the following, so I will use the Raman scattering to show how to identify chiral phonons by the pseudo-angular momentum. And so since in the Raman scattering, the momentum Q is observed in the vicinity of the Berlin zone center. So if we want to observe the chiral phonons, that the momentum Q must have to break both PT symmetry and CNV symmetry. Here P stands for invariant, T stands for the time reversal. So we got two approaches. One is to break invariant symmetry and CNV. The other one is to break time reversal and CNV. So in the following, I will give two material examples for each of the case. So first one is to break invariant symmetry. Okay, so the material corresponds to the elemental material tellurium, which has a C3 screw rotational symmetry along the C-axis, and the phonospectrum is very simple, and it has 3 Raman active modes. And if we focus on the E1 mode, we notice that the W degenerate mode will split into 2 phono modes due to the breaking of invariant symmetry and CNV symmetry. And those 2 branches carries the pseudo angular momentum of +1 and -1. And based on the topological meta theory, we know this E1 is a double wave phono with chain number of 2. So in order to observe the chirality and topology of this double wave phono, so the circular polarized Raman scattering should be used. So 3 conservation rules for the momentum energy and the pseudo angular momentum should be satisfied. And hereafter we got those 3 equations. And the last one is the most important one, as Professor Zhang and Sato sensei have introduced. I will skip this part. So I will show you the result for this E1 mode. So if we use the circular polarized light with sigma plus and minus, then by using those 3 equations, we can only observe the pseudo phono mode with the pseudo angular momentum -1, which corresponds to this green data. And if we alter the polarization of the light, then we can only observe the phono mode with pseudo angular momentum +1, which corresponds to this red data here. So hereafter we can selectively with green phonos with specific chirality and topology by using circularly polarized Raman scattering. Okay, so let's skip this part. Okay, so as Professor Sato has introduced, they also observed the chiral photos in both the alpha phase mercury sulfur and this tellurium. So I would like to note that for the chiral crystals like tellurium, there will be naturally existed 2 enantiomers, which means that if we change the chirality of the crystal structure, then the K-space chirality or the sign of the angular momentum, the sign of the pseudo angular momentum, and the sign of the chain number will all be altered, which means that the chirality of the crystal structure are closely related to those 3 physical quantities. And on the other hand, if we can use any of the physical quantities here to identify the chirality of the crystal structure. Okay, let's move on to the second case, which breaks time reversal symmetry and CNV symmetry. So the material corresponds to the cobalt tin sulfur, and this is the first experimentally verified ferromagnetic well-set metal. And the magnetic order is along this C3 rotational axis. And because there is invariant symmetry in the system, so the Raman, so the phono modes can be cataloged into the Raman active modes and the infrared active modes. Here, the highlighted phono modes are the ones observed by experiments. Okay, let's first start with the Raman active modes. And our collaborators in Tsinghua University observed that for this EG mode, which is doubly degenerate, and if when we decrease the temperature, this EG mode split into 2 phono modes. And if we change the Raman light, and the splitting is due to the breaking of time reversal symmetry and the vertical mirror symmetry. And if we change the Raman light to the circular polarized ones, and in each circular polarized light sighting, we can only observe 1 phono mode with a specific pseudo angular momentum. So furthermore, we flip the magnetic order from down to up, and we notice that when we reverse the magnetic order direction, the phono splitting also reverts, which means that the phono splitting is highly related to the magnetic order. And moreover, we also study the center frequency for those two phonon modes and the frequency difference between these two phonon modes under the magnetic field. And we can see that both of them show obviously hysteresis behavior, which means that the phonon splitting in this material is induced by the intrinsic magnetic order, which is very different from the previously studies where, for example, those materials, in these materials where the phonon splitting is highly dependent on the external magnetic field. Okay, this is for the Raman active mode. Let's move on with the infrared active modes. Actually, I visited Professor Martin Dressel yesterday in Stuttgart University, and we collaborated on this work. So first, our collaborators noticed that in the optical conductivity results, we have observed 4 phonon peaks, and combined with the DFT calculations, we confirmed that all of them belong to this EU mode. Oh, EU mode, okay. So in the following, I will use this phonon mode B as an example because all of them are the same. Okay, so first we observe the phonon absorption at both the temperature above and below the Curie temperature. And we notice that at the low temperature, the phonon peak becomes asymmetric. And this is caused by the strong electron-phonon coupling for this phonon mode B. And on the other hand, we combined with the polar curve rotation measurement, and then we got 2 phonon peaks in each of the circular polarized light channel. And those 2 phonon peaks have different frequency, different asymmetry configuration, and different intensity, which means that the EU mode will also split at the low temperature, and those 2 phonon modes have different electron-phonon coupling. And this is caused by the tilt of the band crossing near the Fermi energy and the different orbital compositions of the electronic band structure. Okay. In the end, we also changed the temperature and observed the phonon splitting for this EU mode. And we noticed that this EU mode also split when the temperature below the Curie temperature. So this is quite similar with the EG Raman active modes that we introduced in the previously slide. So both the Raman active modes and the infrared active modes observed by the experiments shows that the phonon splitting in this ferromagnetic well-set metal is induced by the intrinsic ferromagnetic order through the electron-phonon coupling. However, we only offer the simple model analysis and the DFT calculations which have the time reversal symmetry. So which means that our calculation is inaccurate, but luckily we have a more accurate quantitative calculation based on the molecular barrier curvature theory on this material, and our DFT algorithm can accurately describe the time reversal symmetry breaking and vertical mirror breaking in this system. And this work is in preparation now and maybe appear on arXiv next month. So I still have several slides, sorry. Yeah, so in the following, so I will briefly show you how to use our table to identify Chiral phonons from the experimental data. Yeah, so several material examples very friendly to the experimentalist. Yeah, the first one is the cobalt material, and the momentum Q that I observed in the Raman scattering belongs to the C3 rotational symmetry. So based on our table, we should focus on here. And the phonon modes with pseudo angular momentum +1 and -1, the Raman shifts will split. Yeah, here split. And the angular momentum should parallel to the C3 rotational axis, since the angular momentum is a pseudo vector, which means that the angular momentum for those 2 phonon modes only have the Z component. Okay. Next example is MOS2, and the momentum Q belongs to the little group of C3V, which have an additional vertical mirror symmetry. And in this case, we should focus on here. and the phonon modes with pseudo angular momentum of +1 and -1 should be degenerate. Yeah, here degenerate. And but the angular momentum for each of the phonon mode can take an arbitrary value due to the degeneracy of the phonon mode. And another one is the iron-selenium. Yeah, and the momentum Q belongs to the little group of C4 In this case, there is a phonon mode with pseudo angular momentum of 2, and yeah, we should still focus on this part. And for this phonon mode, which is non-degenerate, so which means that the angular momentum for this phonon mode with PM equals 2 is 0. So which means that this phonon mode is non-chiral. Okay, just by this table. Okay, the last example is a new phenomenon that we discovered during our symmetry analysis, which we call half-wave plate effect. We found that when a system has only a mirror symmetry, and in this case, if the Raman light propagates parallel to the mirror plane, then the circular polarization of the incident light can be reversed by the phonon mode with mirror order symmetry. Let me give you an material example. For example, this black phosphorus, which you might be very familiar with. So the Q, momentum Q that observed in the experiments belong to the little group of C2V. Let's say there is a mirror symmetry in the black phosphorus, and if we use the right-hand circular polarized light, and if the light is scattered by this phonon mode gamma with mirror order symmetry, then we will get a left-hand circular polarized light, which means that the phonon mode B with mirror order symmetry acts like a half-wave plate, and such kind of process cannot be explained by the conservation of the pseudo angular momentum. Okay, so let me make a brief summary here. So we studied the topological and chiral degrees of freedom in well phonons, and we predicted several topological phonon materials, and we proposed that either breaker inverse symmetry or time reversal symmetry can obtain chiral phonons. And based on our work, we have finished a review, and it is under review in the review model physics based on the topological phonon topic and the chiral phonon topic, and the comments and are welcomed. At last, I would like to thank all the theoretical, numerical, and experimental collaborators. Yes, thank you very much. Yeah.
Thank you very much.